My name is Zacchaeus Scheffer, and I am presenting the GabriellaV2 system developed in the Center for Research in Computer Vision at the University of Central Florida. It performs action detection on surveillance videos. For this system, we concern ourselves with untrimmed security videos and aim to detect activities, be they human or vehicle, or indoor or outdoor. The types include both single actor as well as actions involving multiple actors and actions involving an actor and object. To this end, we develop effective spatiotemporal localization that can find the start and end of actions as well as the spatial extent of those actions. Here we have the system overview. First, the untrimmed video is divided temporally into clips. These clips are sent to an object detector which finds all candidate actors. After being filtered, these objects are tracked and sent to the classification network where each object in the clip is given a multi-class label. These labels are then stitched together and split with our TMAS algorithm, and after a final non-maximum suppression step are converted into final predictions. Delving deeper, the localization is performed in 3 steps for a given clip. First, we use the YOLOv5 object detector to detect where the objects are. Then we use a background subtractor to remove stationary objects. Finally, an object tracker tracks which detections are of the same object. Here we have an example of object detection. The YOLOv5 object detector operates on 2D images, so we use its detections every few frames. This creates bounding boxes around any potential person or vehicle actor. For the background subtractor, we use the MOG2 background subtractor because it is simple and intuitive. It reduces false alarm rates by 40% and speeds up the overall system by 200%. This speedup is almost entirely due to decreases in classification time as fewer objects need to be classified. Here we have a prime example where the majority of objects are stationary. Because we are concerned with activity detection, we can safely remove any object which is entirely stationary, as shown here with the missing bounding boxes. The object tracker we use is the sort tracker, which operates on bounding boxes to determine which detections are the same object. The main way it does this is through intersection over area or IOU criteria. In most cases, this is quite straightforward. Suppose the tracker knows about 3 objects, and suppose the boxes here indicate where they were last seen. Now suppose we detect a new object A. Because there is no overlap, it becomes a new track. Call it track 3. Similarly, we might have a detection that overlaps with 0, so it would be added to track 0, and so on. Here we have a comparison of the GabriellaV2 and the original Gabriella localization systems. The goal of the tracklet generation is to have high activity recall. The orange line gives the V2 performance while the gray gives the original performance. When using a ground truth overlap threshold of 0.8, we achieve a 22% higher recall. For action classification, each detection can have multiple labels, so we train a 3D CNN backbone with sigmoid activations on ground truth tracks using a standard BCE loss where we treat each class independently. Action classification needs to be treated differently than in the previous system because tracklets are actor-centric. To do this, we generate tracks with YOLO, send those tracks to the action classifier, and generate labels using the ground truth labels and some spatiotemporal overlap criteria. One problem encountered in the real-world data sets is the very extreme differences in activity counts. For instance, in the Mavid dataset, talking has almost 400,000 instances in the dataset, while abandoning a package happens only 330 times. This is more than a 1000 to 1 discrepancy, so we use partial label masking, or PLM, to deal with these extreme class imbalances. Another important relationship is class correlation. We use log sum exponential pairwise, or LSEP loss, which is based on the BCE loss. This is used with PLM to account for class imbalances. We use knowledge distillation using 5 diverse teacher classifiers distilled into one student classifier to teach the student multi-label action dependencies using what is referred to as dark knowledge in the literature. While the full model ensemble has a baseline of 0.564 MAP, we can distill it into a single classifier that achieves near identical performance, more than 4% better than training the student normally. Here we have a diagram of the training setup with a teacher ensemble and student network. Here the model architectures are the same, so we add a loss that encourages similar intermediate activations between the teacher ensemble and student network, in addition to the normal ground truth loss and knowledge distillation loss on the model output. This diagram shows our setup for model compression knowledge distillation. This is a second stage knowledge distillation where the student in the previous slide becomes the teacher in this slide. We consider a heavy 34-layer R2 plus 1D model teacher which has been trained in the setup before, and an IRCSN 152 student model which we distill using a BCE loss with the ground truth labels and an L2 knowledge distillation loss. Notice that IRCSN 152 is approximately twice as fast. In the table below, you will notice that IRCSN 152 performs 8% worse when trained normally versus using knowledge distillation, in which case it performs as well as the teacher model. Because the model is smaller and faster, we are able to include multiple compressed models in our final Gabriella system. Post-processing is performed in 2 steps. We have our TMAS algorithm that combines tracklet predictions along a track and then creates multiple single-class predictions from a single multi-label prediction. Then a non-maximum suppression step removes duplicate predictions. Delving into the TMAS algorithm, we first take our individual tracklet predictions and chain them together using the tracklet ID as determined by the sort tracker mentioned earlier. Then the track is duplicated for each class which predicts above some threshold. Finally, we have spatiotemporal deduplication. We actually square the detections made by the YOLO network to give consistent aspect ratios to the action classifier. This extended region, as well as the overlapping nature of object detection, causes actor tracks to sometimes include outside actions, so we need to remove extra predictions this creates. To achieve this, we employ a non-maximum suppression algorithm. Here we have an example of an indoor scene. The squared bounding boxes are in green. The red box indicates an area where many bounding boxes cover the same area. Any action covered by multiple bounding boxes has a high probability of producing duplicate predictions. The TrekVid 2021 challenge utilized the VRAT dataset, which uses known cameras. Our system placed second in the challenge overall. Additionally, we submitted our system to the SDL 2021 Unknown Facility Leaderboard. This competition is based on the MAVA dataset and has teams evaluate on videos entirely of unknown origin. We placed first in the challenge overall. A major problem in computer vision is the generalization problem, where a model that performs well on a dataset does not work well in the real world. Here we have a plot of the change in score for various classes when comparing PMIS when the camera facility is known to unknown. Here, a positive score means that the PMIS on unknown facilities was that much larger, so a smaller value indicates better generalization. Our system achieves the best generalization among all high-performing teams. Over time, our PMIS and NAUDC dropped significantly leading up to the end of the SDL competition. Some of the things that caused the most significant drops include using a bigger ensemble with knowledge distillation and the spatiotemporal deduplication step in post-processing. Our system also achieved the best PMIS while being only slightly slower than the average high-performing system, though it still performs much faster than real-time. In conclusion, the GabriellaV2 system achieves real-time performance and generalizes very well to unknown facilities. We built upon our original Gabriella system by replacing the action tubelet localization with actor tracklet generation. We also used better classifiers by accounting for class imbalance, multi-label class correlation, and by using knowledge distillation. We also improved post-processing using NMS-based spatiotemporal deduplication. In the end, we placed first in the active SDL 2021 unknown facility leaderboard, and we were the runner-up for the TrekVid 2021 leaderboard. Thank you.